Regional wildfires and industrial stagnation produce atmospheric haze events that routinely engulf entire city skylines in dark particulate layers. This haze carries chemically reactive, combustion-derived toxins directly into the human respiratory system, creating an acute toxicological hazard. Smoldering biomass and peat fires undergo incomplete low-temperature combustion, producing the specific chemical aerosols found in these events. The severity of the physiological threat is determined by the specific aerodynamic diameter of the particles suspended in the smoke. In a regional fire event, the microscopic, chemically reactive particles capable of traveling hundreds of miles present a greater systemic threat than the localized heat of the flames. Particulate matter is categorized by size. PM10, or coarse particles, measures 10 micrometers or less in diameter. PM2.5 represents the fine, respirable fraction, measuring 2.5 micrometers or less. PM0.1 consists of ultrafine particles measuring 0.1 micrometers or less. In these environments, particulate lethality is inversely proportional to aerodynamic diameter. To identify why high-concentration haze triggers systemic organ failure, we must trace the interaction between these three particle sizes and human anatomy. The human respiratory tract functions as a multi-stage mechanical filter designed to trap airborne debris before it reaches the blood. PM10 is the inhalable fraction. Larger particles are generally trapped by nasal hairs, upper airway mucus, and the mucociliary escalator of the trachea. While coarse particles cause acute irritant pharyngitis and allergic rhinitis, they rarely cross deep pulmonary barriers. PM2.5, the respirable fraction, bypasses these upper mechanical barriers to deposit deep within the terminal bronchioles and alveoli. Once settled, these fine particles induce intense localized oxidative stress and damage the alveolar epithelium. The ultrafine PM0.1 fraction achieves direct translocation across the alveolo-capillary membrane, entering the bloodstream. Because PM0.1 enters systemic circulation, a respiratory inhalation event becomes a blood-borne hazard. Haze is a complex aerosolized chemical cocktail, defined as much by its toxicity as its physical size. This diagram shows a single carbon core. Its massive surface area allows highly reactive combustion-derived toxins to bind to the particle. One major chemical payload consists of polycyclic aromatic hydrocarbons, including benzo-A-pyrene, a group 1 carcinogen known to form direct DNA adducts. Heavy metals such as cadmium, lead, arsenic, and mercury also bind to the surface area of these carbon cores. Finally, reactive volatile organic compounds like benzene and formaldehyde ride these particles into the body, where they induce cellular lysis and severe mucosal inflammation. Ultrafine haze particulates act as Trojan horses, smuggling carcinogens and heavy metals past the lungs and directly into the heart, kidneys, and liver. The physiological consequences of this systemic delivery are divided into acute impacts occurring over hours and chronic impacts occurring over years. Acute exposure triggers a massive release of pro-inflammatory cytokines, which can accelerate systemic inflammatory response syndrome. This inflammation leads to acute cardiovascular consequences, including endothelial dysfunction, microthrombosis, and myocardial infarction. Chronic exposure locks the body into a state of persistent inflammation, leading to accelerated coronary atherosclerosis and ischemic stroke. In the brain, ultrafine particles trigger microglial activation and neuroinflammation, accelerating markers for Alzheimer's and dementia. Long-term exposure to haze is a direct driver of multi-organ cardiovascular and neurological collapse. In active disaster zones, the physical demands placed on first responders create an additional toxicological risk. A human at rest has a minute ventilation of approximately 6 liters per minute. Heavy physical exertion in the field increases this minute ventilation to between 60 and 100 liters per minute. This tenfold increase in air intake massively accelerates the internal accumulation of particulates, causing rapid operational fatigue and vocal cord inflammation. In a haze environment, physical exertion acts as a dosing multiplier that accelerates systemic poisoning. Haze also presents external hazards that degrade the effectiveness of field operations. High particulate density causes me-scattering, where the aerosolized matter physically scatters light. Me-scattering results in a catastrophic drop in visual range, effectively blinding personnel and increasing vehicular collision rates. These conditions ground rotary aviation, while fine ash clogs engine filters and degrades drone optical sensors. Dense haze environments diminish tactical advantages by blinding human rescuers and disabling the technical sensors they rely on. Standard public health mitigation protocols, specifically surgical masks and cloth coverings, fail to protect against these particulates. Because they provide no functional seal, surgical masks allow over 80% of PM2.5 particles to bypass the fabric entirely. Effective protection requires an N95, KN95, FFP2, or KF94 respirator to establish an airtight facial seal. First responders in dense smoke require elastomeric half masks with P100 filters or powered air purifying respirators. For indoor protection, clean air shelters must be sealed at the perimeter and equipped with true HEPA air purifiers rated for 99.97% filtration. Because PM0.1 behaves like a fluid in the air, protection depends entirely on an absolute mechanical seal. Operational planning often fails when it relies on 24-hour averaged composite AQI indexes. Those 24-hour averages obscure dangerous midday concentration spikes that represent the highest risk to personnel. Field advisories should be based exclusively on real-time PM2.5 concentrations, measured in micrograms per cubic meter. All non-essential outdoor physical training must be canceled when ambient PM2.5 exceeds 55.5 micrograms per cubic meter. Survival and operational capability in these environments require treating atmospheric haze as a dynamic, systemic chemical hazard.